We are in week 7, and we're going to be talking about logarithms and the basic properties of logarithms. And you'll need this for this week and next week. So first off, we need to start with the definition of a logarithm so you know what you're looking at here. So the mathematical definition says for x greater than 0 and b greater than 0 and b not equal to 1, then y equals the log base b of x. So that subscript, the small b there, is the base. That is equivalent to x equals b to the y. So essentially, the logarithm is just another way of writing an exponential equation. And it's also used to it's actually the inverse of an exponential equation, and we can use it to undo exponentials just because of this property that it's basically they're kind of going from one to the other. So if you have the equation y equals log base b of x, the thing that the log is equal to is your exponent. The base is the base, the thing under the exponent. And then what you're taking the log of is the number that is rewritten as this exponent. That's what this logarithm is doing. So the value of y we call the logarithm. It's the output when you do the log. B is the base, and then what you're putting into your logarithm is called the argument. So as I said, these are basically equivalent. It's another way of writing an exponential equation. So they're the same thing, they're just two different forms. So one is called logarithmic form and the other is called exponential form. And there is a reason why we have two different forms, because sometimes it's easier to solve something when it's in logarithmic form versus exponential form, and the logarithm is really useful for solving if you have variables in your exponent that you want to kind of get out of the exponent. So when I think of a logarithm, I think, okay, it is the inverse of an exponential. It undoes an exponent. So it's giving you the exponent, and it's giving you an idea of how big a number is. Because if we're looking at numbers in base 10, if you're comparing like 10 to 100, and you put those in exponent form, so, oops, let me get my pen here. So if I'm comparing 10 and 100, I can rewrite 100 as a power of 10. And the logarithm is comparing the sizes of those numbers based off of the exponent. So 10 has an exponent of 1, 100 would be an exponent of 2. And the logarithm, if you took the log of those numbers, it gives you the exponent. So one of them would give you an exponent of 1, the other one would give you an exponent of 2, and the difference tells you how many times larger it is in powers of 10. So the logarithm is giving you an idea of how big the exponent is, which gives you an idea of the size when you're looking at base 10. So if like the log came out to 9, you know that number is in the trillions. Like if it came out to 6, you know it's in the millions, because 1 million has 6 zeros. That would be 10 to the 6th power. So it's giving you an idea of the size of a number. That we use logarithms. So there's another example here. If you have two numbers, x and y, and one has a log of 5, the other one has a log of 3, the difference between those is 2. And if this is a base 10 log, that means that it's 10 to the 2nd power times larger, or 100 times larger. We don't know what the actual numbers are, but we know how many times bigger the one is from the other. That's what the logarithm is telling us. It allows us to compare the sizes of numbers without actually kind of looking at the numbers or caring about the numbers themselves. So the logarithm is really useful when you have really large numbers or really small numbers, because instead of having to count how many zeros you have, you can take the log and it kind of tells you how many zeros you have, or how, it gives you that number. So that's when I think of logarithms, I always think about it's giving me the exponent. It's basically telling me how many times bigger it is in powers of 10, essentially. So there are 4 basic properties of logarithms, and I've got the definition of the logarithm once again up on here because that explains where these properties come from. Because you've never seen logarithms before, you're like, why is log base b of 1 equals 0? Why is that true? Well, if you rewrote it in its exponent form, then it makes sense of why it's true. Because these can be written in either way. If you have an exponent, you rewrite it, it gives you the log. So we'll look at the first one. And when I'm trying to take, we have on the left the logarithmic form of the property. I'm going to take the logarithmic form and convert it to the exponential form. And then you'll see something that you know the rules of exponents, and you'll see, that's why this is true, because when I look at it in rules of exponents, that makes sense. So the way that I convert these is I first start with the base. Well, here is b. And then what it's equal to is my exponent. So b to the 0. So anything to the 0 power is equal to 1. So I know that is equal to 1. That thing that the exponent is equal to, that is what we have inside here. That's how you convert them from logarithmic form to exponential form. As you've basically got your base, you take it to the exponent of what it's equal to, and then that whole answer equals what you were taking the log of. So that's how we convert these. So this would be b to the first power, and anything to the first power is equal to b, which is why we have b here. So if you look at it in the exponential form, that's why we have this property. It's basically we have something that's true, b to the first power equals b, and when we rewrite it in exponential or in logarithmic form, that's what gives us the logarithmic property. This case, we have b to the x, and that equals, well, b to the x. That's kind of silly to write it in exponential form. B to the x equals b to the x doesn't do anything. It doesn't mean anything for us. But having that property in logarithmic form is actually very, very useful. And then the last one is actually something in logarithmic form, and we want to convert it to it's in exponential form, and we're converting it to logarithmic form. So we're actually going the other way. So when we convert it to the logarithmic form, you write log. This is my base, and it's equal to my exponent. So my exponent here is log base b of x. And then whatever this thing is equal to, that is, oops, I didn't write the right base. I wrote x. That was supposed to be b. But then the x on the outside, what it's equal to, that is just what goes inside the log. So again, we get this equation, log base b of x equals log base b of x, which doesn't really mean anything. But when it's in the form on the left, that's actually a very useful rule. So this is how we write all of these into their exponent form, or take the exponent into the logarithmic form. Now let's take a look at what these are all telling us. So just kind of remove my marks here. So log base b of 1 is basically saying the log of 1 is always equal to 0. So it doesn't matter what the base is. If you're taking the logarithm of 1, it's always equal to 0. That's what that is telling us. The next property, the log base b of b equals 1. This is essentially saying that these are basically canceling out and just leaving us with 1. So that's what you want to kind of notice there, is that if you have the base and what you're taking the log of match, they cancel and you're left with 1. And likewise, if we've got the log base b of b to the x, again, the log base b and b, that stuff cancels. What we're left with is the exponent, which is x. So those are two related rules here. And then the last one is basically telling us, well, if you have b to the log instead of the log and then the b, they still cancel out. It doesn't matter the order there. And you're still left with x left over right there. So that's what these properties are saying. We've got that the log of 1 is always equal to 0. We've got if the base and what you're taking the log of matches, you get 1. And if there's any exponents involved, your result is just whatever the exponent was. And then if it's in the other order, you have the exponent and then the log instead of the other way around. You know, just the order of the logs are reversed. It's still whatever that you know, those cancel out. You're just left with your x, whatever your unknown thing was. So that's what the properties of logarithms are telling us. And we'll use these properties and you'll see how it allows us to simplify problems. But that's, in a nutshell, what you want to take out of this. So before we start doing examples, I do need to talk about the natural logarithm. So this is a particular type of logarithm. So the logarithm, which is also another way of writing an exponent, you can have any kind of base. We usually have base 10 because we usually work with powers of 10. But you can have any other base. But the other common base that we have is e, which is called Euler's number. And that, if you have anything that's base e, that's what's called the natural logarithm. So I actually looked up where the symbol comes from, because the symbol are the two letters ln, and they stand for Logarithmus Naturale. And that actually comes from Latin. It's basically the Latin for natural logarithm, but in Latin the words are reversed. So that's why it's abbreviated ln versus nl for natural log. But it's just another symbol. So most logs, we just abbreviate a logarithm with the word log. But if it has the base e, we have a special symbol. And we have this special symbol because it's used so often. So a lot of calculators have a button for the natural log. My calculator has a button for both. It has a button that says log, and then there's a button that says ln. So it's got the natural log as well, because both of those are used so often. In science and math, the natural log is actually used more often than the base 10 log. So a lot of programming languages actually use the natural log. When you program the word and you use the word log, it's actually giving you the natural log, not the base 10 log. So it's just something to be aware of if you're going into like computer science or engineering, that if you use programming languages, even though it may use the word log, they actually are, it's doing the natural log. So just a side note there, that most of the examples we're going to be doing use the word log with the base, but if it uses ln, that's just, it's the same thing, it's just a different symbol because of the specific base of e. So to go back to the properties of logarithms, when you use the natural log, they're slightly different because, you know, we've got a specific base. So the natural log of 1 is equal to 0, just like how I said that the log of anything, the log of 1 is always 0. So the natural log of 1 is 0. The natural log of e, basically the natural log and e cancel out, you're left with 1. If you are doing the natural log of e to the x, then again, the natural log and e cancel out, you're just left with the x left over. And if they're in the reverse order, if it's e to the natural log of x, the natural log, those cancel out, you're left with the x. So the rules are the same, it's just we've got a different symbol because now we're using a natural log symbol, and then the base is specific e. So you just have to keep that in mind when you're working with these. So those are all the actual properties. So now let's actually do some examples and work with these things. So we are going to use the properties to simplify these expressions without using a calculator. So we're just going to, practice using these rules. So this first one, we've got log base 6 of 6 to the 7. So the log is base 6. 6 is the base of the exponent. That stuff is canceled out, and you're just left with your exponent. So that's one of the properties of logs, that the base of the log and the base of the exponent, if they match, it cancels out. When we move to the example on the right, we've got log base d of d, the base of the log, and the base, there's no exponent here, but it would be a 1. Those match. So again, those cancel out, and you're just left with 1. Bottom left, we've got 4 to the log base 4 of a minus c. So the base on the exponent and the base in the log, because they match, that cancels out, and you're left with a minus c. Then we've got natural log. So that ln is the natural log, that's base e, and that always cancels out with an e, which leaves us with the answer x squared plus 1. So simplifying these are actually really simple. It's just a matter of knowing the rules and knowing that things cancel out, and then you're just kind of left with whatever's left over that you see. Are there any questions so far? Okay. So, we're going to move on to some more examples. So log base pi of 1. So the log of 1 is always 0. It doesn't matter what the base is. It doesn't matter if it's pi, if it's 2, whatever that subscript is, it doesn't matter, because the log of 1 is always 0. On the right, we have log, or 6 times the log base 7 of 7. So the log base 7 of 7, that cancels out. So we're just left with the number 6. Because that log base 7 of 7 is equal to 1. That would be 6 times 1, which is just 6. So sometimes what we'll do is kind of, when we cross it out, we'll put a little arrow and then point to 1, saying that that is actually equaling 1. And so then you get 6 times 1. Bottom left, we've got the log base c of c squared. So the base on the log, the base on the exponent part, those match, those cancel out. We're just left with 2. And then bottom right, the natural log and e, you really want to basically memorize that those things cancel out, and we're left with a plus b. So I've been saying all term that basically like weeks 4, 5, and 6 are going to be the worst, and then once you get to weeks 7 and 8, you're going downhill. They're going to be much easier. Hopefully you can see here why I've been saying that the hardest weeks are actually 4, 5, and 6, because like this logarithm stuff is actually not bad at all. It's actually very simple. Are there any questions so far? Okay. So now I'm going to move into some that are kind of more complicated, because we're kind of combining different things. We're adding things with logs, multiplying things with logs, that sort of thing. And so there's a little more work involved with these to simplify them, but it's still not bad at all. So on the left here, we have a log base 2 of 2 plus a log base 2 of 4. So we know from our rules that the log, that Log base 2 of 2 is going to give us 1. So far we have 1 plus the log base 2 of 4. But we don't have a property if the base and what you're taking the log of doesn't match. So what we need to do is, we know that the base of the log is 2, so we want to rewrite 4 so it's an exponent with a power of 2, basically, or with 2 as the base. So you want to try to rewrite whatever you're taking the log of as an exponential expression where the base matches the base of the log. So 4 is the same as 2 squared. So we're going to rewrite this. So that's 1 plus log base 2 of 2 squared. And then we can use that property of logs where the log base 2 of 2 cancels out. And we're left with our exponent here, which is 2. So we end up with 1 plus 2. And this simplifies to 3 as our final answer. So you have to do a little bit of thinking. You have to try to rewrite numbers in their exponent form, which is why we learned how to do prime factorization, rewrite numbers as product of primes. You know, we used that when we were simplifying radicals. That same skill comes in handy here because it allows you to simplify these logarithms. So the example on the right, I've got log base 2 of 2 times 4. So we don't have any rule about if you have things multiplied inside there, but I can multiply 2 times 4 and give me 8 and see what that does. So we've got log base 2 of 8 when you actually do that multiplication. So again, we don't have a rule on how to simplify if the base of the log doesn't match what you're taking the log of. So we want to rewrite 8 as 2 to some exponent because we want to match the base. So 8 is equal to 2 to the third power. So we're going to rewrite this as log base 2, 2 to the third power. And then that allows us to use the property where the base, log base 2, 2 cancels out, and we actually get the same answer, 3. Are there any questions? Okay, so one thing that I want to point out about this example is that it gives us, this is basically demonstrating a new property of logarithms. It's not a basic property, it's a more advanced property of logarithms. But basically, if you have the log base b of x times y, this is the same thing as the log base b of x plus the log base b of y. And so that's why the left side and the right side gave us the same answer, because this is actually a property, a rule of logarithms, that if you've got multiplication inside, you can separate it out by turning it into addition. And this, if you think about the fact that the logarithm is giving you the exponent, when you multiply things with exponents, you add them. So that's why this kind of makes sense. This property makes sense because we've got some things that are multiplied. It's giving us the exponent, so you really add them. So this is an advanced property of a logarithm, not a basic one, but this is one that you will be working with. So a couple more examples on this one. We've got on the left log of 100,000 minus log of 100. So if there is no base written, we assume it's base 10. It's just we use base 10 so often, if there's no number written there, we assume that it's base 10. So this is really log base 10 of 100,000 minus log base 10 of 100. So in order to simplify this using our rules, we need to be able to rewrite 100,000 and 100 as powers of 10 so that we can cancel things out. And so you just count how many zeros you have. So 100,000 has 5 zeros, so that's 10 to the 5th power. So this is log base 10 of 10 to the 5th. And then 100 has 2 zeros, so that's 10 squared. So I can just rewrite these. And now I can use my property where the log base 10 of 10 cancels out. We're left with 5 minus 2, which gives us an answer of 3. So example on the right, again, we've got log. There's no base actually written, so it's assumed it's base 10. And inside we have 100,000 over 100. So I'm going to first rewrite this as log base 10 of 100,000 over 100. So we don't have a rule when we have things, divided inside here, but I can actually do this division. So basically, I'm just canceling out powers of 10. So basically 2 of the zeros disappear here. And this is equivalent to log base 10 of 10,000. I have to count the correct number of zeros there. So now, when this is base 10, we want to rewrite 10,000 as an exponent with a base of 10. So there's 4 zeros, so that's going to be 1, 2, 3, 4, 5. I subtracted 2 zeros. I should have 3 zeros. I wrote, yeah, I don't have enough. I have too many zeros here. 1,000. I'm like 1, 2, 3. There we go. Okay. I think because my cross didn't quite cross out my 0. So it's actually log base 10 of 1,000 if I actually do my division properly. So 1,000 is actually 10 to the 3rd power. So we rewrite this as log base 10 of 10 to the 3rd. And then the base, those cancel out, we're left with 3. So this one also gives us an answer of 3. And this is demonstrating another property of logarithm. That's a more advanced property, that if you have log base b of x over y, if you've got some division, that's equal to subtracting top minus the bottom. And again, if we go back to our rules of exponents, if you've got things with exponents, you're dividing them in order to simplify. We subtracted the exponents top minus bottom. So this is what this is telling us. It's following the same rule of exponents. It's just it's written in a different form because now we're writing it as logarithms versus exponents. But it's the same exact rule. So are there any questions so far? Okay, so now I'm going to step it up. We're going to have logs inside of logs. And you might think, oh my gosh, this looks really complicated. It's not as bad as it seems. You just kind of work inside out, trying to simplify. And once you've simplified the inside, then you simplify the outside, and you go from there. So on the left, we have log base 16. And then inside there, you have log base 81 of 3. So we want to simplify the inside out. So we want to simplify log base 81 of 3 first. So what we've done so far is with the properties of exponents, we've tried to rewrite things to be the same base. So if our base is 81, we want to rewrite 3 as 81 to some power. But I don't know what exponent, I don't know, 81 to what power gives me 3? I don't know. Like, that's not something that you know off the top of your head. So the logarithmic form here and the property based off of the logarithm, well, that is not helpful because we don't really know how to rewrite that. So it actually will be more helpful to put it in its exponent form. And that's why you want to be able to go from one form to the other in order to simplify, because sometimes the other form is more helpful. So we've got inside the parentheses, we have the log base. Actually, let me match the color here. Log base 81 of 3, and we don't know what that's equal to. We don't know what it simplifies to. If I convert that to the exponent form, I've got the base of 81, where it's to the exponent of x, because remember when I was doing those conversions here, 81 to x, and then whatever we have left over there is what it's equal to. So that's equal to 3. So this is the same question we had. 81 to what exponent gives us 3? How do you rewrite 3 as 81 to some power? And off the top of your head, you don't really know that. But by actually writing down the question we're asking ourselves here, 81 to what exponent gives me 3, we can start using our rules and what we know about exponents. So 81 is 9 squared. So 9 squared to x. And with our rules of exponents, you multiply those. So this is 9 to the 2x equals 3. So, okay, we can rewrite 9. 9 is 3 squared. So we've got 3 squared, and then to the 2x equals 3. Our rules of exponents say we multiply those. So that would be 2 times 2x, so 3 to the 4x equals 3. So the exponent on the 3 here is 1. So if the bases are the same, then the exponents must be equal. So 4x must equal 1. And this, then if we solve for x, we find out that x is equal to 1/4. So I have now found out that the log base 81 of 3 is equal to 1/4. So now I'm going to rewrite my equation. And actually, I clearly don't have enough room here. So I am going to slightly modify what I've got here. Give me a moment. I'm going to just make some changes on my slides. And okay, so I just kind of moved the second problem. Let's just kind of ignore what we've got here. That's going to be now on a new slide because clearly I don't have enough room. Okay, so we have found out that log base 81 of 3 is equal to 1/4. That's what we kind of figured out using what we know about exponents. So now I've got the log base 16, and we have just discovered log base 81 of 3 is 1/4. So now we've got log base 16 of 1/4. And we're trying to say, okay, what does this simplify to? So let's just say, okay, this equals y. What does this simplify to? So I'm going to do the same thing I did before. I'm going to convert this to the exponent form and see if that helps us out, to see if we convert it to its exponent form, because, if you're just thinking about this, I don't know, 4 it isn't, you know, I'm trying to rewrite something to have an exponent of, or a base of 16. I can't really do that. So when we rewrite this as an exponent, it becomes 16 to the y is equal to 1/4. So, okay, I've got 1/4. And if you recall about our rules of exponents, you get reciprocals when you have a negative exponent. So if I change the exponent to a negative y, this gives me 4. I can take the reciprocal. So this helps us out because now, okay, 16 is 4 squared. So I've got 4 squared to the negative y equals 4. So you follow my rules of exponents. 2 times negative y, I get 4 to the negative 2y equals 4. So 4 just has an exponent of 1. This tells us that negative 2y is equal to 1. And so then when you solve for y, you get negative 1/2. And so that's what this has just told us. What we just did was we found that the log base 16 of log base 81 of 3. So we found that the log base 81 of 3 is 1/4. So this is the same as log base 16 of 1/4. And we just found out that that gives us negative 1/2. So we simplified this expression without using a calculator. And what we used is the rules of exponents, or basically the definition of an exponent, or a definition of a logarithm, sorry. We took our logarithm, we rewrote it in its exponent form, and then we manipulated the exponent so that way we can get the bases to be the same, because that's the whole goal with logarithms, is you want to have the same base. And then that allowed us to set the exponents equal to each other and solve. And then because we had this embedded one inside another, we had to do it twice, because we had to do the inside logarithm first. And once we figured out what that was equal to, then we had to do the outside logarithm and kind of go through the same process until we got our final answer. So are there any questions on this? Okay. So I've got another one here. I took my second one and I just made it in a separate example here. I'm going to show you a different way that you could try to do the same problem. I don't know if this is going to make more sense to you than the way that I did the previous one. I mean, it's not the same problem. It's a similar problem. We have log base 4, log base 16 of 4. So I'm just going to show you a different way that you can think about this. Don't know if it will help, but it might, you know, because this kind of stuff is a little bit confusing. So this example, I worked inside out. I rewrote it in its exponent form, did some math, plugged it back in, rewrote it in exponent form, did some math. For this example, I'm going to instead try to use only the basic properties that we had, where we try to cancel out the base of the log with the base of the exponent. And I'm going to try to be really creative about it. And I don't know if this will, you know, kind of work for you, but we'll see. We'll see. So just like the other example, I'm going to be working on the inside first. We want to kind of simplify this log base 16 of 4. So I'm going to start by that. We don't know what this is equal to. Now, previous example, I rewrote this in exponent form. In this case, instead, what I'm going to do is take that base of 16 and rewrite it as a power of 4, because we've got 4 that we're taking the log of. So we have log base 4 squared of 4. So we do not have a rule where you can cancel out, like we don't have a rule with logarithms where if you have an exponent in the base that it equals, the base of 4 or whatever like that. So we're looking at this, and I can try to rewrite this as I want to rewrite this 4 as 4 squared to some exponent that is going to get me back to the 4. And I want a 4 squared as my base. So this is to the negative, not the negative, the positive 1/2 power. So this is taking some really creativity. This is really creative, takes some brain power. This may not be a method that necessarily works for you, but what I'm doing as I've got my 4, the main 4 that I'm taking the log of, I'm trying to get the bases to match, so that way I can use my property of logarithm and they can cancel out. So I'm doing this little side thing where I'm saying, okay, how do I get 4 to be equivalent to 4 squared to some exponent? So I just have to kind of mentally think, what exponent do I need there so that it cancels out the 2 and I just get back my 4, which is what I've got right here. So an exponent of 1/2 will cancel out the 2. So I rewrote this as 4 squared and then the 1/2 power. This allows me to then, now the bases match, this matches, so now I can cancel this out, and this gives me 1/2. But I'm not done, because we were given the problem log base 4 of log base 16 of 4. And I've just simplified the log base 16 of 4 to equal 1/2. So now I want to try to do the same sort of thing here. So I can't really write 4 as 1/2 to some exponent, or 1/2 to like 4 to some power. That's a little bit hard, but I can say, okay, I've got 4, which is equal to 2 squared. So I took my base of 4. I'm now rewriting this as 2 squared. And I want to take this 1/2 and I want to rewrite it as 2 to some 2 squared to some exponent. So the reciprocal of 1/2 is 2, and that would be if it's 2 to the negative 1 power, because this is 2 to the first power. So really, I'm looking for an exponent, a way that I can rewrite this so that if I rewrite it as 2 squared, I get an exponent negative 1. So I need to replace this with a negative 1/2, because 2 times negative 1/2, those cancel out, and that will get me negative 1. which is the same thing as 1 over 2. So this is really getting it into advanced kind of like understanding exponents, the negatives with exponents, that sort of thing. But then that gives us log base 2 of 2, and I've just determined that 1/2 can be written as 2 squared to the negative 1/2 power. And now I can use the property where the base, those all cancel out, and I get us a final answer, negative 1/2. So it's a different technique than the technique that I did here. Both methods work. So you could have done that problem by rewriting these sort of in their exponent form, trying to rewrite the exponent, figure out what that missing exponent is or what you need to have, and then you have these equations. Or you try to rewrite the logarithm and then rewrite your values so that the bases match, so that way you can cancel things out and get properties of logarithms. So this method, it takes more steps, but I think it's easier for people to understand. This method is much shorter as far as what you're writing down, but mentally, I think it's harder on your brain because you really have to think about your exponents and you're trying to manipulate numbers into something else. And that's hard for a lot of people when they're learning algebra, So this method the second method that I showed really requires a lot more critical thinking and problem solving than the first method does. You have to think about how to manipulate numbers to get them in the form that you want. Now, if you can do it this way, this is a fantastic skill to have because it's really thinking out of the box and trying to make things in a way that works out, that's easier. But if this is the method that, if you're not there yet, this method works completely fine. We're just using we're getting the same answers, like we're doing this, there's two different methods to solve these. It's just a matter of, do you want to try to use the basic properties of logarithms, or are you willing to write it in its exponent form and then manipulate it looking at it in the exponent form and see what you can get? So, yeah, two very different, the problems have different numbers, but the way you would solve these would be the same. It's just a matter of which method to use. So, are there any questions? Okay, so I will tell you that like these type of problems, these last two types of problems, you're not going to be like quizzed on these. These are just, to help you see and work with the basic properties of logarithms. Most of the stuff you're going to be using, the basic properties of logarithms, are going to be these other examples where you've got things that are subtracted or divided or, added, multiplied, or just these basic kind of things. So rarely are you going to see things where you've got a logarithm inside of a logarithm. These are just good problems to kind of get your brain thinking and to really practice those rules. But you're not going to be quizzed on it. You're not going to see those complicated things on the homework. So that's all I had. So hopefully, from the very beginning stuff with the logarithms, you see they're not so bad. Those last two problems really get your brain working, but the rest of it, not bad. What you're going to be doing on the homework and quizzes this week and next week, not going to be bad. You know, it's going to be pretty straightforward. So that should be a relief for nearing the end of the class and getting some things that are really not going to be too bad. So if you do run into any questions, you know how to reach out to me. And hopefully you enjoy your weekend. And I will get this posted before I have to leave to my thing at 3, which is why I moved this a little bit earlier, just to give myself enough time since I have something later this afternoon. So I will try to get this posted before I have to leave. So, all right, thank you very much. Take care.